depending on your course, this could be the last chapter. I'm going over chapter summaries for matter interactions. I'm on chapter 11, angular momentum. So let's just step back for a second and look, right? Where have we been? There's three huge ideas in this course. And the first is right here, the momentum principle. This says that the net force on an object is the derivative of momentum with respect to time, or the rate of change in momentum. And a lot of times we will write this as F net. As a finite change, dp, delta p, delta t, and then we'll do some cool stuff with that. But you could, if you let delta t go to 0, you get a derivative. Either way is fine. And then momentum, if it's going slow, the momentum is mass times velocity. If it's going very fast, you have to include that gamma factor that depends on the speed of light. But let's just stay slow. Let's just slow down for a second and not do that. That's one big idea. And then we had all these forces that we could calculate. We had rates of change in momentum for an object moving in a circle. It was just a lot of great fun. And then the next big idea is this. It looks really short, and it seems that way, but it's very powerful. And this is the work energy principle. This says that the work done on an object is equal to its change in energy, where work is the dot product of force and displacement. And then the energies, you can have kinetic energy, potential energy, depending on your system. You can have a real or point particle system, a bunch of great stuff. Super powerful. So now we're ready to move on to the last idea. And that is the angular momentum principle. So I'm going to go ahead and write that down. I'm going to write it. Angular momentum principle. It says this. The torque net about some point O vector is the derivative of angular momentum with respect to time. So right there, it kind of looks a lot like this. Instead of force, we have torque. Instead of the rate of change of momentum, we have the rate of change of angular momentum. But what the heck is torque? What the heck is angular momentum? Now, this is just a review. These concepts are pretty complicated, okay? So, read the book, practice stuff, ask questions. So don't think that this is it. So first, let's define torque. You know about torque, right? Because if I have a door right here, and then there's a hinge, this is looking at it from the top, and you come in, you're going to push away, you're going to push right here to open the door. You're not going to push at the hinge. You know that the further you push from that hinge, the easier it is to rotate. Because the further you push from that hinge, the greater the torque. And in fact, we can think of torque as a rotational force. It depends on the applied force and the vector location, RO, that's point O, from the point of rotation to where the force is applied. So it's both of those. And with that, we get torque about a point O. You have to define the point, because if I change the point, I'll have a different torque with that same force. Is RO cross F. And we've already seen vector operations. We saw the vector dot product. Vector dot of vector gives you a scalar right up here. And so this is the vector product, also known as the cross product. It's an operation between two vectors that gives you another vector. So let me give you the formal definition of this, and then I'll give you a more conceptual version of it. So let's go up here and talk about that. And suppose I have two vectors. A is AX, AY, AB. They could be anything, AZ, right? It could be force, it could be whatever. And I have another vector B, BX, BY, BZ. Now, just as a reminder, if I take the dot product A dot B, what I do is I take the X component and of the two vectors and multiply them together, plus the Y components multiplied together, and so forth. So it's going to be AX, BX, plus AY, BY, plus AZ, BZ. So since all these components are scalars, when I multiply them together, I get a scalar. When I add them, I get a scalar. So this is a scalar answer. And these could be negative. You can have negative X, Y, Z components. So the dot product could be positive, negative, or 0, and that's all fine. And then you could also write this as A dot B is the magnitude of A times the magnitude of B times the cosine of the angle between them, if you know that angle between them. That's the dot product. And some people get offended when you call it a dot product, and so it's a scalar product. Well, you can call it whatever you want, it doesn't really matter. Now for the cross product, vector product, we have those same two vectors. If I have A cross B, the way I calculate that, and I'm not going to say why, but I'm going to tell you, it's the determinant of the following matrix. If I take a matrix with x hat, y hat, z hat, ax, ay, that's the x, az, bx, by, bz, then that's going to give me my answer. So let's go ahead and take the determinant of this matrix. So to find the determinant of a 3 by 3 matrix, you need to expand about one of the rows or columns. So let's expand about this. So if that's the case, I'm gonna first take x hat. And so this x hat, I cross that out, and I take the determinant of this 2 by 2 multiplied by x hat. So that means that these scalars multiplied by x hat will be the x component. So I'm going to say this is AYBZ minus AZBY. And if you don't remember how to do determinants of matrices, it's not a big deal. I give this equation for the result after this, so you don't have to memorize it. Now I'm going to expand about the y column right here. When you do that, because of its position, you actually get a negative sign. That means that really this is going to be this times that minus this times that. So it's going to be AZBX minus AXBZ. And then finally we expand about the z, so we get this 2 by 2 matrix, and I get AXBY minus AYBX. And that's the cross product. Now, a really important thing to note here is that, because you're going to use cross products in the next physics course a lot more, because when you calculate magnetic fields, when you do Maxwell's equations, you have to use cross products. Number one, this is a vector. Although each of these components are scalars, put them all together, it's still a vector. So you're taking an operation between two vectors, and you're getting another vector. Number two, what would happen if I did B dot A, it doesn't matter, right? It doesn't matter if I switch the orders up here. I get, it's the same as A dot B. But that's not true right here, because if I switch the order of these two vectors, I'm going to get the opposite. So in fact, A cross B is equal to negative B cross A. And finally, you'll notice that the x component here does not depend on any of the x values. The y component does not depend on the y values. The z component does not depend on the z values. So that means that if you have a vector in the x and y, two vectors in the x and the y direction, the resultant is only going to be in the z direction. So you cannot do this in 2 dimensions. It has to be 3 dimensions. Okay, so now for the shorter version of the cross product. So I can write something similar to this. I can say the A cross B magnitude is equal to the magnitude of A times the magnitude of B times the sine of the angle between them. And so it looks a lot like that, except this one you don't have to take the magnitude because it's already a scalar, and this has cosine, that has sine. The other important thing is, and I should have brought a prop, and I don't have my little vector prop. I had a little vector prop somewhere, but I'm going to just do it with my hand. So if I take 2 vectors, let's just draw an example. A, B. If I do this, I can find the direction of A cross B, and let's say A cross B is equal to C. So the direction of C. So the direction of C has to obey 2 things. Number 1, the vector C has to be perpendicular to the vector A and perpendicular to the vector B. And in this orientation, there are only 2 vectors that satisfy that. One of the vectors is a vector that comes out of the page like this, right? That's perpendicular to A, and that's perpendicular to B. And then the other one is one that goes into the page. And when we draw vectors, we often write this as a vector going into the page, in page, and this out page. So you can remember this as an arrow coming towards you. You see the tip, arrow going away from you, you see the feathers in the back. So the only two vectors that could be perpendicular are coming out of the page and going into the page. And now we pick which one with our right. This is my right hand. We're going to use our right hand, and you got to flex it like this. So what you want to do is take your right hand, and if you let your fingers curl through A and then B, your thumb points in the direction of the resultant. So in this case, if I want to do A cross B, I would do this. And see my thumb's pointing into the page, so it would be that way. You don't have to do this right-hand rule if you do this. This gives you the vector direction. It's not a huge deal in this chapter to calculate torque and angular momentum as a vector, but it does come up, and it does come up more and more. So just make sure you do that. The trick I tell my students is if you're doing the right-hand rule and you're right-handed, put down your pencil, right? Because you don't want to try to do it with the pencil in your hand, or you'll use your left hand, and that's wrong. If you're left-handed, which I'm not, then you don't put down your pencil. Okay, that's torque. That's cross product. So now we're back to torque. So the torque is R cross F. You can see that if I move if you look at the magnitude, torque magnitude about point O is the magnitude of RO times the magnitude of F times the sine of the angle. You want the torque to be a maximum. You want theta to be 90 degrees because this will give you 1. And as RO decreases, the torque decreases. If you increase R, you increase the torque. That's why if you have if you're working on your car and you have a bolt that's stuck, you can get a cheater bar which extends the length of your wrench, and you can apply a greater torque with the same force because you're increasing the value of R. So that's torque. And like I said, if we think about these two things related, the torque is like the rotational force. Think of it as rotational force. Okay, what about the angular momentum? Let's talk about the angular momentum now. So you'll notice it's the rotational momentum. So, one of the things up here, force changes momentum, and momentum is a property of an object that depends on the mass and the velocity. Torque changes the rotation of it, and we can describe the rotation as the angular momentum, which depends on, again, the mass and the velocity, if you have a point mass. So let's start with a point mass, because point masses can have angular momentum. Let's think about a comet orbiting the Earth. My paper's stuck together. Oh, no, the sun. It's orbiting the sun. Comets don't orbit the Earth. Well, they could, but. So here's the sun. And then here is a comet. It comes in like that. And what happens as it gets closer to the sun? It increases in speed. And you could see that from Kepler's second law. You could see it from a lot of different things. But we want to have something conserved, something that's constant in this system. And that constant thing is the angular momentum. So if I take, and let's call this my point O, and I take the vector R, right here, RO, and then I have the momentum vector, P, then we define that's an R vector. Then we define the angular momentum as RO cross P. And it turns out that right here, you'll notice that RO gets very small, so P has to get larger in order for the angular momentum to be constant. Okay, so you can see here that angles do matter. You can write this in a bunch of different ways, but if I have a vector value for that and a vector value for P, I can do R cross P. It's a cross product. I can do R cross P right here. And what you would find is in this system, if the sun doesn't move, which it doesn't really move because of a comet, then the angular momentum would be conserved, and that's how we calculate the angular momentum. It doesn't even have to move in a circle. It can still have angular momentum. Here's the great example. Suppose I have a point O right here at the origin, and I have an object moving at a constant velocity, so it has a constant momentum right there. It still has angular momentum. And in this case, the angular momentum is actually constant, because although here the R is greater than it is right here, you'll notice that the length of this, if we call this the angle theta, this is actually this is r0. This is the magnitude of r0 times the sine of theta, which is the same thing we get. So we do the cross product with this. We get r0 sine theta, or r0, that length, which is r0 sine theta, times p, because they're 90 degrees. But you'd get the same thing here. So you get the same thing no matter what. If I have the object passing right through the point, then r would be this vector, and p is that way. They're in opposite directions. And it turns out that the cross product would be 0 because you can say that's a 180 degree angle. The cosine sine of 180 degrees is 0. Okay. So if we have a collection of masses that are all connected together in some way, and they're rotating with some angular velocity omega, then we could say r cross p for every one of these, and they could have different momentums, right? Because they're different distances. Here's one that's further away, different distances away. We actually did this when we talked about rotational kinetic energy in a previous chapter. We could also describe the angular momentum L as I omega. And remember, I is the moment of inertia. So the moment of inertia for finite sets of points is defined as the sum over I of mi ri squared. So let's see, if I need to take each mass and take its distance to the point of rotation squared and then add all those up. And so we can get this we can do this for continuous distributions by turning this into an integral. But I'm not gonna. I have videos on deriving moments of inertia of different objects. But we have things like a solid cylinder of mass m, radius r. I is 1/2 m r squared. If you have a disk, a hoop that has, like a ring, then I would be m r squared. If you have a sphere, then I would be 2/5 m r squared. And I actually have a video deriving that one too. So if we have a rigid object, we can define the moment of inertia. This is like the rotational mass, right? Because this looks a lot like P equals mv. So angular momentum, rotational momentum, rotational mass, rotational velocity. So there is some symmetry going on here. Now, finally, the angular momentum of a system we actually write as, suppose I have some point O and I have a disk that's moving this way and that disk is spinning that way. I need to talk about angular velocity. I'll do that in a second. Omega P R. Then the total angular momentum of this system, L, would be the translational angular momentum plus the rotational angular momentum. And so this is actually rotational angular momentum. And then we can say L translational is RO cross P. So this has some center mass motion, is moving, plus it's rotating. Both of those would contribute to the total angular momentum. It does indeed matter. So the angular momentum of an object, we again use the right-hand rule. So if I have an object like this and it's rotating this way, the angular momentum, the angular velocity is in the same direction as the angular momentum. So you can use your right-hand rule. If I take my right hand and put my thumb in the axis of the rotation, my fingers will curl in the direction of omega. So in this case, rotating that way, omega would be a vector going into the board. Now, just a quick note about this. This is for fixed axis. So this means that the angular velocity and the angular momentum have to be in the same direction because the moment of inertia is a scalar value. If you take another physics class, if you take classical mechanics, what you're going to learn is that the moment of inertia is not a scalar, it's actually a tensor, and you can have the angular velocity and the angular momentum in different directions. And it makes for some really cool, awesome things that can happen, but we're not going to do that in this particular course. Okay, I think that's it. I know it's a lot, but it's good. It's all good. And again, chapter summary, not chapter understand everything. And I didn't work any problems. I'm going to work some problems too, but this is just a refresher course on angular momentum.